Hey folks, it's Michael Johnson. Welcome to this week's Energy Sketch. We're going to talk a little bit about the scale of energy, the scale of the energy storage challenge. And what I'm showing in front of you here now is a screenshot from Google Earth, sort of 3D exploration of the Earth from Cushing, Oklahoma. The Cushing oil hub where oil is stored and traded. And this is the scale of energy storage that we do today with hydrocarbon fuels like oil, diesel, gasoline, kerosene, as well as other storage systems that exist around the world today for natural gas, gaseous fuels. So I want to get a feeling for the scale of the energy storage challenge and compare this, what we do today at industrial scale with these giant storage terminals. Each of these containers is 60 meters in diameter and 20 meters tall. And we could go into the numbers about how much energy that is and what that means. But what I want to do today is just compare this against a couple of concepts that you see flying around the web. You might have seen something like this recently. Thermal energy storage and gravity energy storage. Here on the left is the polar night energy, basically a silo full of sand that gets heated up during the day using wind, solar, or hydropower, and then that energy can be sort of released at night when there's no solar power. This is the idea. Similar idea here on the top right, energy vault, using blocks of concrete and lifting them up high and relying on that gravitational energy to store our energy and then drop the blocks down to ground level when the energy needs to be taken out of the storage. The problem with these is that they really just simply do not scale. And here at the bottom right, I've shown a quote from a paper, and the link is in the description. So if you take a given mass of that diesel fuel that I was showing you that we store at industrial scale today, you would need to raise that mass up 4,600 kilometers to make its gravitational energy, what's being used in this energy vault concept, equal to its chemical energy. 4,600 kilometers. This thing is not even 1 kilometer high, this energy vault thing. So it just does not scale compared to fossil fuels. Now, regarding temperature, again, this concept on the left is sand, hot sand, storing energy in hot sand. Now, to match the energy in that mass of hydrocarbons, you'd need an equivalent mass of water that you would heat up from absolute zero to 14,000 degrees Kelvin. And this thing on the left only goes up to about 600 or 700 degrees Kelvin. So again, thermal energy storage like this will never achieve the same scale on which we store and trade energy today in the form of hydrocarbons. But don't worry, all is not lost. This paper is focusing on one particular technology and one vector of energy storage, which is in metals, and we'll get to why that is in a little bit. So let's look at this graph now from the same paper. References is in the description. These are the two ways that we can measure energy storage. The important metrics. On the vertical axis is the energy density. So that's energy content per unit volume. So per barrel, per meter cube, per liter, in this case, on the y-axis, the vertical axis. And on the horizontal axis is the specific energy. So that's the energy per unit mass. And I've highlighted here typical hydrocarbons that we know today, that we trade today, that we store at industrial scale today. That's diesel, gasoline, those are liquid fuels. Coal is solid fuel. LNG is liquefied natural gas, and CNG is compressed natural gas. So the LNG is in the liquid state, hence it has a higher energy density on a volume basis versus the compressed natural gas, which is just a pressurized gas. So these are the kind of ballparks where we are able to store energy today. And let's think about some of the concepts that are coming up. One of them is hydrogen. And so hydrogen is at the far right of this graph in its raw state, either liquid or compressed as a gas. So very high specific energy per unit mass, but fairly lower energy density per unit volume compared to the hydrocarbons. The problem is when you try to store that hydrogen into any sort of container, you immediately come way down far on the x-axis. from here down all the way down to here. And this is a aspirational target from the Department of Energy, the United States Department of Energy, for hydrogen storage. And we're not really yet close to achieving that aspirational target either yet. What else is on the menu? Well, batteries, lithium-ion batteries. Lithium itself is a very, very energetic metal, as you can see here, comparable in energy density and specific energy to diesel, gasoline, and LNG. The problem is that it can't be stored really or transported or used in an industrial way to produce power in its raw form. So it needs to be packaged into batteries along with the electrolytes and the other associated dead weight. So sadly, lithium, this very bubbly, very energetic metal, when it's contained into a battery, its energy density and specific energy essentially goes to zero. Slightly greater than zero, but on the scale of fossil energy, it's zero. So we will never really store, transport, or trade energy around the world the way we do with hydrocarbons today in batteries. You could never really ship a ship full of batteries. It wouldn't have enough power to reach its end state, its end goal, its end destination. So the other vector that's proposed here is metals like boron, beryllium, titanium, aluminum, silicon, magnesium, iron, and zinc. And some of these are more common than others. Specifically, iron is very common at industrial scale, also aluminum. And so these have quite a good specific energy and energy density compared to fossil fuels. And so this is why this paper particularly promotes this idea of metal fuels. And I personally agree. I believe that we can be storing and transporting energy in metals, in pellets or powders of metals at a scale that can compare with fossil fuels, but also be decarbonized. So I hope you learned something today about the scale of the energy storage challenge, folks. And remember, gravity storage and thermal energy storage are good on their own at small scale, but they will never scale up to the industrial levels that we trade, store, and transport today in fossil fuels, liquid fossil fuels today. So take care. Be well, folks. See you next time on the Energy Sketch. Toodaloo!